Hi, I'm Jon McLoone. I'm Director of Technical Services at Wolfram Research Europe, and I'd like to share with you a vision for a multi-paradigm form of data science. Quite often when I meet people in data science and look at what they're doing, actually it's statistics. It's various forms of counting. Now, things have scaled up much bigger and there's a lot of work involved in getting big data together and organizing it and doing that on an industrial scale. But the actual computations they're doing are still basic statistics. So if data science isn't the same thing as statistics, what is it? Well, my definition is fairly vague. It's data science is computation with data. But coming from a Wolfram research background, the key there is the computation, because there's this huge corpus of knowledge in computation that is not just statistics, it's all of these other areas like image processing and signal processing and network analysis and queuing theory. And all of these tools are now automated in software that you can wield on your data to produce greater insights and richer results. So let's talk about what computation gives you. One thing it does is it helps you generate more information to do statistics on, so we can find new things to count. Here's a couple of fun examples I just threw together to try and illustrate what I mean by this. Here's a bit of basic counting that I did to help my daughter with her homework project. She was writing about Lord of the Flies, and she wanted to have some data on which characters were mentioned in which parts of the book. And that's just a counting exercise. We went through and we counted the words Jack, the Beast, and Ralph. These are the three main characters of the film. And you can see the frequency once it's smoothed out, coming out here with the Beast dominating in the middle of the book, and Ralph being at the beginning and resurging at the end, and Jack being dominant right after the Beast. And if you know the story, this sort of makes sense. But I realized that we could go a little bit further than counting by looking at things like the sentiment in the book, which is a little bit harder to quantify. You can't simply go and count nice words. But once you bring in things like sentiment analysis, text analysis, and machine learning, well, then we can use things like a machine learning classifier on the sentiment of each sentence. So I did this little piece of code here where I took the sentences of the book. I classified those as the probability that they were a positive sentiment. And if we ask for the maximal of those, then we can go through and find the sentence in the book that is most likely to be positive. So it's sifting through the whole book now and thinking about each sentence. And what we get is the result of we're going to have fun on this island. It certainly sounds like a pretty positive sentiment. So once you add that information in and throw that on the plot as well, now we get a cumulative running total of the current sentiment of the book. And you can see it starts pretty negative where they're shipwrecked. It becomes very positive while they're exploring the island. Around the time that the Beast is discovered, things become a bit more neutral. And then as Jack, the antagonist in the book, becomes dominant, things become a bit more positive as Ralph returns, and things end very badly for everyone involved towards the end of the book. So being able to see this kind of contextual knowledge that's hidden in the data, in the end it was just counting, but to get there we needed much richer computation like sentiment analysis in order to achieve the thing to count. Here's another little personal project I did just to give you a different context. This actually is still in the family. This was my wife's work on needleless injection systems. This is a microscope image of particles that one day will be drug particles being blasted into skin. And she wanted to analyze how well the particles had penetrated and what their distribution was. In the end, that's a counting exercise, but there's a whole language of image processing that we can call upon in order to find the things to count, which are these little black blobs. So here's the kind of image processing process that I did. Was I would take the blobs and use filters that are available in image processing, such as how far from the edge of the blob are we? So here's the distance to the edge of the blob. And then we can find the maximal points within that, which allows us to resolve blobs even though they're touching. And then we can use pure counting on those. And here is the image with those points identified. So you can see through a fairly small amount of rich code, I can measure the components, their centers, and place the little styled X's on each of the images. And then once we've got that data, we're back to statistics and we can count them and find the density. So here is the profile of the penetration of these particles. Now, in the end, that's just a histogram of data. very statistics oriented. But to get there, we're going through a language of image processing. And there's all kinds of different ontologies that we can process in similar kinds of ways in order to extract out the things that we might then do statistics on. Another key thing that we need is to be able to inject context. We need to be able to take our data, but we need to be able to add other kinds of data or to compute other kinds of data that's relevant or related to the data in order to give it more meaning. Let me show you a fun small example here. This is an API that isn't served up by us. It's the current state of the bike system in London. So we've got latitude and longitude and the number of free stands and the number of bikes. And we can see that a little bit better if I put it into the Wolfram Language's native format here. So I'm just converting that JSON over into our own data, and we can see all of the information nicely laid out. But it's not very easy to understand. We could do stats on it like the average number of bikes or the average number of free bikes pretty easily. But in order to appreciate it from a human point of view, then we want to add in the geographic context. What does the latitude and longitude mean? Well, that's a pretty straightforward thing to calculate. We can do that as a geographic projection onto a map background. And here we can see the current state of the bike system. This is the proportion of available bikes per stand across London at this very moment. And you can see that because we're in the middle of the day as I'm recording this, that the bikes are mostly in the centre of London, and all around the edge, the commuters have taken them all and ridden them into the centre. But only through that addition of map information and the computations required to know how to use the geographic projections so that latitude and longitude are correctly placed on the map, are we able to make human sense of this data in this simple visualization. And when you add to that all the other kinds of external context you can inject from different fields, whether that's financial trading prices and economic data or current weather data, to augment the data that you're collecting, that's a key aspect that you need to make sure you can achieve within whatever system you're doing your data science. Another aspect that you need computation for is changing the point of view. We have a tendency to take the data as we're given it and then look at the data. But by transforming the data, whether that's by things like map projections, you can put them into a completely different state that allows you to see aspects that aren't immediately obvious in the data. Let me try and make sense of that with some examples here. So here's some data I was given by a group involved in supersonic cars. This was data on the RPM of the front right wheel, effectively a proxy for the speed of the vehicle, and the position of the suspension, how far down on the suspension the car was pressed. And they said, make something of this data. So I can plot it straight away. It's fairly straightforward, and there's some things you can immediately see from it. You can see how fast the vehicle got to and the timings of it. But some of it's a little bit harder to interpret. But by injecting new viewpoints, you can extract new perspectives. So one fairly simple bit of computation, we can apply some calculus. We've got the velocity there, but if we change that into the rate of change, we've got the acceleration. And immediately you can start seeing interesting features popping out, that there are these stepwise changes in acceleration, an easing off, and then a massive shift here. And actually, when you add in the context of another one of their data streams, here was the position of the throttle in the vehicle during this run, you can see why that makes sense, that the driver of this vehicle has put the accelerator up in steps, which has then caused jumps in the acceleration. They've reached their maximum speed, they've had the foot fall down, and as the air resistance builds up, the car eventually reaches a maximum speed, and then they've taken their foot off the accelerator, and suddenly the car's hitting the drag and going to kind of a full reverse. And then you get some wind down at the end where he finally takes his foot off as it cruises to a stop. But jumping into a different context, I started thinking, well, let's look at this from a signal processing point of view. There's all kinds of computations there. What would happen if we hit this same data with some signal processing computations? And so I took the suspension load and I did something called a wavelet transform on it and produced this wavelet scalerogram. Now, effectively what that's doing is putting it into a frequency space. So this is higher frequency at the top and low frequency at the bottom, but watching that change over time. And suddenly features popped out that are not at all possible to see in the original data. And the engineers who were looking at this, it made no sense to me as I was staring at the picture. I thought it looked nice. But they said, wow, I've never seen that before. Do you know what this is and this is? That's the wheel going supersonic. And as it breaks the sound barrier, suddenly you get this spike in high frequency vibrations, and then this sort of moment as it passes through the barrier where all of the vibrations settle for a moment, and this is the period within which the wheel was going supersonic. And then there's two other interesting features that show up when the final brake is put on at the end after the parachute deployment. And that kind of thing isn't possible unless you bring these seemingly unrelated bits of computation to bear on your data. As well as being able to transform the viewpoint and change the coordinate system that you're using and these kinds of transformations, sometimes you can actually inject completely new viewpoints. Here's a little example from a finance context. So one typical thing that you want to do with a portfolio is to have it diversified, and that means having assets that don't all move in the same direction at the same time. So here's a typical basic bit of statistics that is often done, is to find the correlation between assets. And this table shows some of the correlations that have been calculated. So this asset, of course, is completely correlated with itself, but it's not very correlated with this second asset. In fact, it's slightly negative correlated, which is perhaps a good thing for a portfolio. But of course, the numbers are hard to interpret. So typically what will happen is they get shown as something like a heat map, and you get to see the points at which there's high or low correlation. But it's still not really very informative. On the right-hand side, though, I've added something from a completely different field of computation, graph theory. And graph theory is all concerned with networks like communication networks or social networks. And one typical computation within social networks is to find graph communities, the relationships between families. So if I set a threshold of the level at which I'm interested in correlation, we can immediately now pick out all of the assets that are moving as a family. And the tooltips here show us which they are. This BIOS and Andy are all part of a group of about 8 assets that seem to be moving as a family. They're the most correlated to each other, but you can see which ones are correlated to each other, which are kind of the black sheep of the family, kind of on the edge of the group. And here we've picked out 3 different groups that move as families. And that's a perspective that just looking at the numbers or the straight visualization of the numbers can't give you. And it's a conceptualization that allows you to start thinking differently about the assets, that when you start making your investments, you can start thinking about which groups you want to invest in and which members of those groups are most or least correlated to each other and to others in a very tactile, visual way. Now, another typical problem for data science is to figure out what's signal and what's noise. We often do things like smoothing and averaging to get rid of noise, or doing statistical hypothesis tests to see if things are significant. But I want to show you another place where bringing computation from a completely different field can allow you to extract knowledge from data. So this is very much from noise in its literal sense. So the task here was to take some sound and extract some useful information from it, which ought to be data science, not engineering. Here's the sound. The idea is it's a vehicle passing. And as it passes, we can hear the sound change. And from that, we can construct a speed camera that works entirely on the sound of the vehicle. Now, actually, the way to do it's similar to an example I've shown before. I can convert that into frequencies, and you can see here each of the different frequencies bending over time. We can then run through that with some basic signal processing to find out what the average shift in frequency is, which we get here. But then you can jump to another field, which is modeling. And we can start looking up things like the model for Doppler shift, which is the effect that we're hearing through the sound. You can get that straight off Wikipedia. You have a formula for it, and we can start doing model calibration against the data that we've selected out from the signal processing. So we're starting to join up lots of different areas of computation. But the net effect is we can take that sound and in the end extract out the parameters that are meaningful within that model. And here's the key parameter. The velocity was 19.5 meters per second, so about 40 miles an hour. And the vehicle came within 5.5 meters of the observer. All of that knowledge is in the sound, but you need computation to take it out. So why is it that most data science really is just statistics and various forms of counting? Well, there's a human reason for that and a somewhat technical reason. On the human side, you have to know what's possible. There's an educational barrier there, that there's this huge collection of computation available in automated ways, but you've got to know it's there to know that you can call upon it. And because our education is very focused on knowing how to do the computation, you don't get to cover that many different fields in the time that you have in school. But also, partially on the human side, but with a technical solution, computation can be difficult. So really the frontier at the moment is to try and automate computation as much as possible. The first level of automation is to be able to run an algorithm on the computer. And that's largely been solved across the board. Pretty much anything that is computable is computable in an automated way. But the second tier of automation is to automate the knowledge required to drive that algorithm. Often there are many choices of algorithm on how to solve a problem, and can we automate that educational barrier of knowing which is the right thing, which is appropriate for which circumstances? Well, at Wolfram we've been trying to do a lot of that, and I'll show you a couple of fun examples just to show that in action. Supposing I want to make a predictive model from some data, and here I've got the manifest of the Titanic. Let's have a quick look at that data. You can see the passenger, a first-class 29-year-old female, and she survived the sinking of the Titanic. So that's our data. And we want to do some machine learning on this in order to make a predictor. Well, I might know that I want to do machine learning, but there's 6 or 8 perfectly reasonable ways that I could go about machine learning, methods like logistic regression or nearest neighbor or neural networks and so on. Well, our approach is to say that's automatable. We can put in algorithms to help you find which is the right algorithm. And so when we say classify that data, that's a task, not an algorithm. The algorithm in this case has been chosen for me automatically. It's chosen the naive Bayesian method. It's decided for some reason, which I guess I don't need to concern myself with, that that's the best method for a set of data that's got a couple of thousand points, is a string, a number, and a string in a triple. Now, multiplying that up over all of the different possible algorithms is a monumental task, and in some places it's more automated than others. Things like parallel computing, still quite hard to figure out how to automatically parallelize algorithms. Things like differential equation solving, we can pretty much automate whether you should be using the Adams or Runge-Kutta method, so you never need to know these details as a user. And the aim in the end is to make computation not just available through automated algorithms, but accessible through automated choice of algorithms, and always raising that level so that you simply need to focus on the answer and the insight that you're trying to reach. And here's the result of that after this single command of classify, I can now take an unseen piece of data like a first-class 46-year-old male and make a prediction of that person. Or I could look at all males who are traveling in first class and look at their ages and see what that does in this model that we created. But none of the details I need to concern myself with. Now, of course, there are expert users who can do better, and so we allow you to roll up your sleeves and say, okay, I'm going to decide the method, and I'm going to decide that we're going to use random forest as a method and build a new classifier. But that shouldn't be the first step. That should be only for experts or those who are trying to refine that extra bit out of performance, who should know details of computation. You should be able to start without any detailed knowledge. And that kind of automation extends itself across not just things like algorithm selection. Things like pre-processing data and getting things into a computable form are all part of automation. So here's a different example, but actually it's not different at all. I'm going to take photographs and try and predict whether they're nighttime or daytime scenes. But as a user, I just do exactly the same task, classify. The fact that these are photographs and perhaps need a different method and perhaps need pre-processing to turn the photographs into a set of key features to recognize, that's all automated for me. I just again say, here's the data I haven't seen, make predictions from it. So the more we can do of that, and the more we can automate the production of code and the steps that make the whole workflow, automating import, automating export, all of these things, the less work and the less knowledge required and the more productive somebody can be. And any system that aspires to have this sort of whole multi-paradigm data science approach has to take care of all of these issues, or in the end, you're driven by the effort of coding and the burden of knowledge to fall back to the same subset of things that have typically been used in data science for years. The ultimate aim of ever-increasing automation is to automate not just the computation, but the acquisition of insights. And machine learning is perhaps one of the the examples where it's at the forefront of being able to do this, of extracting knowledge without humans really needing to know how they're looking for that knowledge. So let's look at an example of this actually in action, that for a long time the idea of identifying images was a human-driven operation, but machine learning has made it so that we've gone much further without actually really knowing the details of how it's done. So let's see what that's capable of doing right now. Here I've got my webcam attached to the camera, and you can see that it's recognizing a person. But if I hold up some objects here, then hopefully it can figure out what those are. A tea urn, that's a pretty good guess. And perhaps if I hold up another object, a cup, and there is no human coding in here to say what are the features of a tea urn or a cup. Sometimes it's a little odd in its interpretation. My blue shirt here, it's decided are medical scrubs, but you can see why it might think that. But through an entirely automated process, we can start extracting knowledge from, like, the contents of images straight away, straight out of the image. Now, there's levels to this. One is a kind of supervised layer where we as humans at least tell it the direction we want it to be thinking. Let me show you a fun example of how I can do this in practice. I'm going to teach the computer right now how to recognize rock, paper, scissors. So if I turn on the webcam here and hold up my impression of rock and tell it to start watching, I'm going to capture 10 images of rock. I'll move it around a bit so it gets some experience. And then when we get to about 10, we'll show it's paper, and we'll get 10 or 12 of those. And then once we've got enough data there, we'll go and show it scissors. And then once we've got enough of that, we'll stop capturing and we'll train the machine learning classifier. So that's all the experience I've just given it. And you can see now that it's decided that that last one, as it already knew, was scissors. But if we put it into watch mode now and hold up some images, it says rock, paper, scissors. And you can see in a fairly small amount of experience, it's doing a pretty good job at recognizing what it is that I'm holding up without having to give it any particular guidance apart from the data. And actually, let's have a quick look at the code that I wrote to achieve this. Most of it's interface code. The actual work being done in the button that I clicked at the end there was just that command that I showed before, because the automation means I don't actually have to give it any more guidance than the classes that I showed it the pictures were in the first place. Now, as machine learning research makes further advances, we're moving more and more into the world of no supervision at all, a completely hands-off-the-wheel approach to data science. So here's a data set of dogs. They're just a bunch of photographs of different breeds of dog. And what I want to do is to take that and have it put those onto a plot and group them according to the features that it sees. So there's no data here at all. The dogs are just pictures of dogs. I haven't even told it they're dogs. But what it's able to do is to go through that data set and look for things that seem to distinguish and be common between different images, and then form clusters within it. And you can see in an entirely automated way, it still doesn't know they're dogs, but it's managed to figure out that all of these images have something in common. So all of these little white handbag dogs have all been grouped together. And down in the bottom left corner, we've got some big hounds that have been put together, and some beagles and basset hounds have been grouped together here. And so it's achieved quite a human insight of grouping these pictures with no knowledge at all being provided from me, apart from here's 150 pictures, go and do something useful with them. So let's look at that in practice, how automation can help us with this process of building apps and deploying them. So here's the analysis that I did earlier. I just copied the code over. This was the bit that imported data on a bike system and injected some geographic context and then visualized it. But I'm going to add a little bit more wrapper to this to describe an extra menu to make the thing interactive as a user. But the rest of the programming, the kind of update events and all of those things, we can automate. We can figure that stuff out behind the scenes and produce this app that can live either standalone or in the document. And now I'm not just limited to seeing the current state of London, but I can choose from hundreds of different cities. And let's choose, for example, Abu Dhabi, and we can see the current state of the Abu Dhabi bike system. Now, that app at the moment is living within what we call the CDF, the computable document format. And that means downloading a player or having a copy of Mathematica to use it. So it's nice, but it's not really deployed. But what we can do, because we have a symbolic representation of the the logic of the program and a symbolic representation of the interface, we can push that to this cloud-based server by just taking the app that we've created and saying deploy that, and I'm going to give it public permissions, and that means that anyone in the world could use it. I could set it up to be private so that only I could look at it or some named individuals, but here I've made it public. And it's generated a URL, which if we go now to a website that has defined, and once the thing has initialized, what we should see is exactly the same application in the cloud. And there it is. And we can interact with that just as before and pick different cities and go and look at Abu Dhabi again. But this is now operating in the browser and accessed only using standard web technologies. So that's only possible because of an automation for translating that into HTML5 and JavaScript and things that web browsers expect from the symbolic representation. That kind of automation can also be brought to bear on more system integration issues. If you need to make your algorithms or data science available to systems across an organization. And actually the process is pretty similar. The idea is that I can cloud deploy, put it on a website, but this time I'm going to put up an API that can be accessed from other programs. I have to give a bit of information here because RESTful APIs aren't very intelligent about types, so I have to tell it that there's going to be 3 arguments and what type they are. But now I'm just going to call that Titanic survival function that we created earlier and make that available as an API. There it is on its URL. I can then point any program I want to that knows how to consume an API. One example, of that would be to use it as a backend to some computation within a spreadsheet. So if I jump now to a remote Windows computer, then you can see I've got access to that algorithm through this Wolfram API function that lets me call the web service. And now I can do computations using that machine learning classifier, but that's being done entirely within Excel. Or not entirely within, it's passing the work off elsewhere, but it appears to be within Excel. And again, it's because we have a symbolic representation of the classifier and the program, and a symbolic representation of API functions allows me just to push all of that in one go to the cloud, and we've got this instant creation and deployment of an API. So the whole workflow from getting data in, doing your analysis, using all kinds of different computation, deploying it to an API and making it available to other programs can be automated from beginning to end. So if we want to use the most powerful data science, this multi-paradigm data science, and get the best insights, I think my messages are quite simple. The toolset is huge. It's more than just things that sit classically within the statistical sciences. Make use of them. There's all these different contexts that things have been developed for, but they apply outside of the sciences that they were made for. And it's automation that makes that toolset available to you. And at Wolfram Research, through the Wolfram Language and programs like Mathematica, we're doing our very best to drive the cutting edge of that automation forward to make it ever more powerful, but ever easier to use for somebody who has at least a basic technical education. And in the end, this isn't a threatening thing, automating all of this work that is so cumbersome to do. It's liberating. It allows the human to rise to a higher level to seek the insights rather than spend their time choosing computations and doing computations. We can focus on the questions and getting the answers that we want from the data and getting richer and richer conclusions. Thank you. I've been Jon McLoone, and I hope you enjoyed this.